Hi, everyone. My name is Oge Okoronkwo. I just graduated from the University of Oklahoma, my undergraduate degree in astrophysics. And this summer, I've been working in the CCA with my mentor, Dr. Allison Brooks. And I've spent my time here understanding isolated LMC mass analogs and their satellites. So the goal of this project is to identify isolated LMC mass galaxies and analyze their interactions over time using two different databases, one from the Romulus simulation and then another one using high-resolution Zoom simulations. So to start off with just a little bit of background, what is the LMC? So the LMC is the Large Magellanic Cloud, and it's a dwarf galaxy about 10 times less massive than the Milky Way, and it is the largest known satellite of the Milky Way galaxy, aka our home galaxy. And so what is considered a satellite? So a satellite is anything or a smaller companion galaxy that orbits a more massive and more luminous host. And you can consider any galaxy to be isolated if it's not bound by the gravitational potential of another galaxy. So the current state of the LMC is not an isolated galaxy because it orbits the Milky Way. And so here we want to understand the distribution of the satellites around an LMC mass galaxy. So this, let's see. So this picture right here is a mapped image of all of the stars in the Milky Way galaxy. And if you can see here, these two little fuzzy spots. So this here is the LMC, the Large Magellanic Cloud. And then this tinier one here is the SMC, which is the Small Magellanic Cloud, and it is the satellite of the LMC. Not very creative, but that's the name of it. And so here on this image down here at the bottom, so basically scientists have been using like photometric surveys to find smaller galaxies around the Milky Way. So it's believed to be that there are like hundreds of satellites of the Milky Way. However, it's not identified which of those are belonging to the LMC or the Milky Way. So basically, this project is about how many satellites in the Milky Way are actually from the Milky Way itself or from the LMC. And so in the dark energy survey, which is this picture here, you can see imaged the LMC and the SMC here. And this is a dark matter map, which is where it's estimated to believe that there are hundreds of other dwarf galaxies located. So I've had the help of the Romulus 25 simulation, which it's a large volume of cosmological simulation, and it's 25 megaparsecs per side, and it contains thousands of galaxies, anywhere from groups to Milky Way-sized galaxies, dwarf galaxies, clusters, and so on. And it basically gives us an idea of galaxy evolution in different scales, and there are different environments that you can explore. So here imaged is basically the full simulation in this bigger blue box. And then from this spot right here is an LMC isolated galaxy. So these are basically the simulations or the types of galaxies that I'm going to be looking at. And so from the Romulus database, we were able to find 333 different isolated LMC galaxies. And there were about 59 satellites that were located. And in this picture here is an example of a simulation of one isolated LMC mass galaxy. And so it's plotted in terms of virial mass. So enclosed in the larger white circle is the host galaxy. And as you can see, this LMC mass galaxy has 5 different satellites, all in red circles enclosed. And then from our database, these are mass distributions of the 59 different satellites. So most of the satellites or most of the LMC analogs had at least one satellite. However, if you notice, within the histogram, it says that 10 of them have 0 satellites, which actually isn't the case. Romulus can't really find dwarf galaxies that are smaller than 10 to the 7th solar mass. So this is where the zoom analogs come in handy because they can locate and image dwarf galaxies, which are faint and ultra-faint dwarfs. So we were able to I was able to examine 4 different high-resolution analogs. However, only 3 of them are pictured here due to computing troubles. But yeah, there's HALO 431, 597, and 488. And these are all in distributions of stellar mass. So the darker areas represent where there are higher densities of stars. And so high-resolution analogs are very handy because they're a tool used to study faint and ultra-faint galaxies, as mentioned earlier, and they can resolve internal dynamics going on within the galaxies. So quenching, distributions, and any different like host to satellite interactions going on. So maybe there are different like gravitational interactions going on. And looking at the zooms, we can basically study that deeper than we could with using Romulus. And so here is an image of a comparison of Romulus to the high resolution simulations. So basically all of the gray triangles that you see are all of the different LMCs or isolated LMCs from Romulus. And we were able to cross-examine from the Romulus database and the Zoom database galaxies which like matched up from each database, if that makes any sense. So the blue triangles that you see are virial and stellar mass ratios from Romulus, and the stars are the zooms. And as you can see, the stars or from the zooms are higher in virial mass and stellar mass because it was able to pick up those smaller stars that Romulus probably wouldn't be able to find or locate because they are so small. So basically, this is just a confirmation that what we wanted to get out of our high resolution zooms, we are actually getting. And here are satellite luminosity functions. So on the left side is the Romulus satellite luminosity function in terms of stellar mass. And so we have the number of satellites compared to stellar mass. So as you can see again at the bottom, in terms of stellar mass, it goes from 10 to the 7th all the way to 10 to the 10th stellar mass. And with our satellite luminosity function of HALO 431 that was imaged earlier, it's 10 to the 5th all the way up to maybe like 10 to the 7th solar mass. So our zoom-in analogs are able to show that we're able to pick up smaller satellites and smaller distributions that Romulus would not be able to tell us. So for future work, I plan on studying what the dominant quenching mechanism is for LMC satellites, and I have already begun to do that. So here in this graphic here is basically a tidal index, which measures disruption within a satellite. So basically different gravitational interactions that are going on between the more massive and luminous host and the smaller satellite. And so the higher the tidal index means that there's more disruption going on. And then I also have an image here of star formation history versus time. So are these satellites still forming stars? Are they still active? If they're not, that means they're quenching, or basically your galaxy is dead or dying. And so the more smaller LMC-sized galaxies are still star forming. However, the slightly larger ones are quenching quicker than we expected. So future work would be studying studying the quench fractions as a function of definition and mass. I would like to give a special thanks to the Simons Foundation and NSBP for sponsoring this research. Also, a huge thank you to Dr. Allison Brooks for her mentorship and allowing me to be part of the project. Also, thank you to Faram Munshi, Jordan Van Ness, and Claire Riggs for being collaborators. Also to Casey, Saran, and Shannon for arranging this whole program. I'm super, super grateful. Any questions?
All right, great. Are there any questions in the room for Oge? Yeah, Nathnia? Can you use your seat mic so that people on Zoom can hear? Press the black circle, it'll pop up, and then when you see a green light, you can talk.
Okay, can you hear me all right?
Yeah, I can hear you.
So I was wondering, whenever you were like talking about like the quenching mechanism, is that like talking about? I'm just like a little unfamiliar with that. Is just like how the galaxy is like being
Yeah.
stretched and which way? Like, how do you
Exactly.
quantify that?
Yeah, so there are different terms of light quenching. So there's strangulation, ram pressure stripping, and tidal stripping. So it's basically just like a removal of gas, and even sometimes like the stars will get pulled away from the galaxy along with the gas, leaving the dark matter halo like in disarray. And same for the gas. If there's no gas in a galaxy, then stars aren't going to be formed because that's basically the fuel that's needed to produce more and more stars. So the galaxy is basically like dying at that point. But yeah, maybe my guess is that there is some like relationship between how far away the host is from the satellite, or maybe if they're close together, then something, I don't know, might be disrupting them.
That's very interesting. Thank you.
Yeah, Tony?
Hey, my question is what is the source of the disruptions you mentioned? Is it the host galaxy or it's the LMC?
Yeah, I believe it would be the host galaxy.
Jury? There you go.
I was wondering, like, what is the correlation between, like, the quenching and then star formation in terms of, like, the age of the galaxy? So if stars have stopped forming and you're saying that means that it's old, like, could it also mean, like, they haven't formed yet, so they're going to, so it's young? Like, how do you determine the difference?
I guess you could determine based off of what stars are within the galaxy. So if the stars themselves are older, you can assume that the galaxy is within like a certain age range. However, I don't know. I haven't quite started looking into it yet, but I feel like if I want to assume that just because you're having like gas stripped away doesn't necessarily mean that the galaxy is old. Like it could just be like it's within a close proximity to the host. Like so, yeah. Hope that answers your question.
Yes.
All right, great. Let's thank Oge again.